All right, hello everyone. So we are back for more 7.2 Infinite Series, and I think that I will start with a quick recap of some things from last time. And I won't go over everything, but let's just make sure that we remember the main points. First of all, we had the definition of series. And it's an infinitely long sum, and it could be written with sigma notation, which would look like this. And what it really means is A1 plus A2 plus A3, and so on. So it's an infinitely long sum. And then we talked about what it means to converge. We say that it converges to S if the limit of Sn equals S, where Sn are what we called partial sums. And S would be some finite number. And it diverges otherwise. So let me underline converges and diverges. Now, here's what I want to say. We're going to see a lot of problems in this chapter that are basically going to give us some infinite series in some kind of form and ask us, does the series converge or diverge? And technically, this is what determines if it converges or not. But in practice, we usually are not going to look at the partial sums that often. We're usually not going to look directly at the partial sums. We're going to come up with other rules and shortcuts and ways of figuring out if certain series converge or diverge. And we've already started to do that. And that was with geometric series. So we have a rule that we came up with. We spent a while deriving a rule because it's an important one. Well, first of all, what is a geometric series? So it is one that is of the form AR to the n minus 1 for some constants A and R. All right, and the rule that we came up with for geometric series to determine whether or not a geometric series converges, it depends on what R is. And if R has an absolute value less than 1, and that's another way of saying this. It's another way of saying that R is between -1 and +1. Then the series converges. Not only does it tell us that it converges, but it tells us what it converges to. This little formula, A over 1 minus R. And otherwise diverges. So every series is either going to converge or diverge. It has to do one of those. So if we have a rule that tells us when it converges, then we could just say otherwise, if it fails to meet that condition, we can say it diverges. All right, so if we have a series of this form, we can look at what R is. And I think we saw one problem last time, or one example series last time, that was a geometric series that when it was first written, it didn't look like this form, but we had a way of kind of getting it into this form. So, all right, this was kind of my recap. It all fits on the screen. And now I want to show you another example of a geometric series. So here's where the new stuff begins. Now, I think for the next couple of examples, I'm not going to write out the entire question. The question that we're interested in is, you know what, I'll write it for one of them. I'll write it once. Does the series converge or diverge. If it converges, find the sum. Okay, that way I wrote it at least once today, but that's the general question that we're most interested in. And here's the one for this example. Okay, so we haven't really seen that many series yet, and the idea is that series are going to fall into different categories, like some series are geometric series, and some series are some other things we haven't talked about yet. For now, we don't have a lot of tools, so maybe this is a geometric series, but in the form of a geometric series, the exponent is supposed to be n minus 1, and the exponent that we have here is n. So we want to figure out what we can do about that. And there's this little trick, and I think we did this in one example last time, and we're going to do it again, is that if we want that to be an n minus 1, we can pull out one of the 4/3. And now it's an n minus 1. So the idea is that in the original series, we have n copies of 4/3, and what I did was I pulled one of them out front. In fact, I could even put a little exponent of 1 here, right? I mean, this is 4/3 to the 1, so you could put a 1 here if you want, and then if you add those exponents, it adds up to n. So, yeah, these are equal. We didn't really do too much yet, but the nice thing about doing this is it fits the form of a times r to the n minus 1. That's the form that we wanted. And now we could say this is a geometric series with, well, let's figure it out. R is 4/3, so we have to just figure out, is this true or not? Is R in this interval? And no, it is not. It is not. So let's say absolute value of R is, well, absolute value of 4/3. 4/3 is greater than 1. So it diverges. And that means that this does not add up to anything finite. There's no finite sum that this adds up to. All right, so that's a good example of a geometric series problem. And by the way, when a problem is phrased this way, I didn't really write it, but it's sort of implied that you need to show enough work to justify your answer. You know, because converge or diverge, it sounds like a 50-50 chance that you get it right. You know, flip a coin, does it converge or diverge? Well, no, we want to see you explain why, justify your answer. So in a series problem like this, I'm not just looking for diverges. You know, I think a big part of the grade would be all of this explanation. And don't be afraid to write some sentences. I mean, I know it's a math class, and sometimes students don't like to write sentences in math, but you kind of have to explain what's happening here. All right, but we didn't have to write that much. I think it's good the way we wrote it. All right, let's do another. I'm going to get a fresh sheet of paper for this. All right, my next example, it's the same question, so I'm not going to write the question again, but a different series. And this one is sort of similar. All right, take a look at this series. All right, so it still has a 4/3, but this time the exponent of n is only in the denominator. So what I want to say about this is this geometric? You know, it's not written in the form of the, definition of geometric, but we've seen that sometimes a series can be like rephrased. So maybe there's something we can do to make this look like the form it needs to be. So it doesn't look like it at first. But maybe there's something we can do to rearrange it. So let me show you what I'm thinking. First of all, the 4 up top is just a constant. It's just a number. So I could just pull the 4 out front, and I could say 4 times 1 over 3 to the n. You could do that. That makes it look a little bit closer to the form we want. In fact, I could do this. I could say 1 over 3 to the n like that. So let me just say real quick what I just did. In my first step, I pulled the 4 out front, and that left me with a 1 up top. In the next step, I pulled the exponent of n out of this fraction, and the reason it's okay to do that is because when you have a fraction raised to an exponent, you would raise the numerator to that exponent and the denominator to that exponent. But the numerator is 1, and 1 to the n will always be 1. And that's what makes this okay. So 1 to the n up top, 3 to the n on the bottom. It does equal the previous step. Now, it's almost the form that I want for geometric series, except I would want this to be an n minus 1. So we do what we did on the previous one, which is pull out one of the 1/3. One of the 1/3 gets moved out like that. Okay, well, now I feel like there's 3 numbers here, a 4, a 1/3, a 1/3, and it's so close to being that form. So let's just do one more thing. Combine these, right? Combine the 4 and the 1/3 to get 4/3. I didn't really need that last set of parentheses, but it's fine. Fine to have extra parentheses. Yeah, I did this 4 times 1/3, and I made it 4/3. And now it's exactly in that form, right? So this is the form a times r to the n minus 1. So it took some work, and we might not always have to write out every single step like that. You might be able to skip, maybe skip this step, or, you could probably find 1 or 2 of these steps to skip writing. But, all right, so I'm going to say geometric series with, let's write it like this. A equals 4/3, r equals 1/3. That's what we found over here. Since the absolute value of r is 1/3, which is less than 1, the series converges. I'll put a big box around that. That's part of my answer. And it converges to, let's find this, a over 1 minus r. So put in a, I need a 4 up here, 4/3, 1 minus 1/3. And we'll simplify that and figure out what that equals. Up top is a 4/3, on the bottom is a 2/3. That simplifies to 2. So that's a good answer. That's a good answer. And I think everything we needed to say is explained. Also, we made it clear. We're clearly stating our answer. It converges. Here's why it converges. And here's what it converges to. This is the sum. So that entire series, if you were to add up all of those terms, infinitely long list of things that we're adding up, it adds up to exactly 2. By the way, when you do one of these, I would like you to somewhere put the phrase geometric series. That's going to become more important later as we're going to have other types of series that have their own name. And, this is us saying this is the kind of series we identified. This problem is this kind. And that's why it's okay to use this rule. Okay, let me show you something before we move on. Also, so we answered the problem. I like the way we wrote it. Everything looks good. But I want to show you another way to think of this problem. What would happen if we write out the first few terms? Now, something that I am going to say every once in a while is we've talked about sequences in 7.1 and series in 7.2, and it's important that you don't get them mixed up. Don't mix up series and sequences. But when we talked about sequences, it was sometimes helpful to write out the first few terms, and maybe with a series, it might also be helpful, just to get a sense of what's going on. Like, what is this series? So, first few terms with plus signs in between them, right? So when n is 1, it looks like this. When n is 2, it looks like that, 3 squared. And then when n is 3, it looks like that, and so on. And that keeps going forever. By the way, what we found is that if you keep adding these up forever, you get 2. What I wanted to show you is as you go from one term to the next, each one is times 1/3, times 1/3, times 1/3, right? It's the previous term times 1/3 is what gets you to the next one. So I'll say, notice that every term is 1/3 times the previous one. And this is what it means to be a geometric series. It means there's some constant that you keep multiplying by to get the next terms. And actually, from the way I wrote this out, we could actually figure out that A is 4/3 and R is 1/3. Because R is going to be that constant. The number that you keep multiplying by, that's what R is. And then A is really the first term. So that's kind of another way to figure out A and figure out R. I like the math that we did up above to figure out A and R, but this is maybe a way that you could double check it, or another way to understand it. All right, so that was just more of a little side note, I guess, but we did answer the problem. That was just a little discussion. All right, so next up we have a theorem. This is just one sentence theorem. It's a fact about series. It says if the series is convergent, if a series, this is just any series, okay? This could be a geometric series or it could be something else. Just if any series is convergent, then the sequence of ANs converges to 0. And I want to underline two things here. I want to emphasize that we're talking about a series and a sequence, right? And they're not the same thing. So the series where you add up all the ANs, and the sequence is where all the ANs have commas in between them, and you look at the limit. Well, this is saying that for any series that converges, the sequence of its terms must converge to 0. I'll give you an example. My example is right here on this page. We said that this series we worked on in that example, we said that the series converges. So Is it true that because that series converges, the sequence of terms converges to 0? Well, yes, it does. Actually, we wrote out the first few terms here, right? But you can see that these terms, 4/3, 4/9, 4/27, 4/81, those terms are approaching 0. If you keep going, 4/81 is already getting kind of close to 0. And you keep going, it will ultimately converge to 0. So, yeah, for every series, you could look at sort of a corresponding sequence of its terms. Now, there is a big fact that we're about to say, and it's based on this theorem. It's kind of a way of taking this theorem and rephrasing it into something even more useful. All right, and this has a name, and it is called the test for divergence right away. I'm just going to tell you it's also known as the nth term test for divergence. And it's also going to be a single sentence, and it says, if the limit of an does not equal 0, or the limit of an does not exist, then the series of ANs is divergent, period. All right, so let me put a big box around this. This is pretty important. Let's say we're going to use this potentially all throughout the chapter. So where we're at in this chapter is we want to look at different kinds of series. We want to figure out if they converge or diverge. Later in the chapter, we're going to see some other things that series get used for, because it seems very abstract. Like, what do these things actually get used for? We'll see that later. But for now, we're interested in whether they converge or not. And this is a test. There are going to be other kinds of tests we need also. But for taking a series and having some kind of rule for testing whether it converges or diverges. So far, I would say we now have two rules, because we have the rule that we could use for geometric series, and then we also have this rule that we could use for any series. If this happens, then we know the series diverges. I'll show you an example. And this is not going to be a geometric series. This is not one that we could rephrase into that form of geometric series. All right, is this series convergent or divergent? We could even say the rest of it, if it converges, find the sum and show work to justify your answer. Okay, well, I just said the test for divergence, so I'm going to use it. Let's check the limit of an, where an would be the nth term. So n cubed over 10n cubed plus 7n plus 3. So we've seen limits like this before, right? This is like a polynomial over a polynomial. N's going to infinity. The degree is 3 up top. The degree is 3 on the bottom. So there's that shortcut that you can use where you take the number in front of n cubed up top, the number in front of n cubed on the bottom, and you say, well, that limit equals 1/10. That's a little shortcut because the degree is the same. You take the coefficient 1 up top, 10 on the bottom. Or you could also use L'Hopital's rule. It would also get you 1/10. And 1/10 does not equal 0, right? That's what I was checking. Is this limit not equal to 0? Yes, it is not equal to 0, so the series is divergent, period. I'll say by the test for divergence. That way it's clear. I'm justifying my answer. That's how I know it's divergent. All right, so that's a pretty quick test. Now, it's not always going to answer a question for us. Let's talk about that. Be careful. The converse, this is sort of the opposite in a sense, the converse of the test for divergence is not necessarily true. In other words, the limit of an equaling 0 does not always imply that the series converges. All right. Maybe I shouldn't have put the word always there, but anyway, it's fine the way it is. Yeah, if the limit does equal 0, like if you had a series and you checked the limit and it does equal 0, it is not okay to conclude that the series converges. So the test for divergence only works in one direction. If it's not 0, you say diverges, final answer, that's perfectly fine. But if it does equal 0, you cannot conclude anything. You can't conclude that it converges, you can't conclude that it diverges, and that means more work is needed. We need some other tests, we need other things. Maybe we look at the partial sums. You need some other kind of strategy to finish that problem. So let me elaborate on this. So in fact, if the limit of the ANs equals 0, it means the series might converge or might diverge more work is needed to determine which. In this case, we may say the test for divergence was inconclusive. All right, so it's a good test because if it works pretty fast. You just check the limit. Sometimes you can conclude that a series diverges, and then you're done. But it's not foolproof. It's not going to answer every problem for us. All right, so let me get a fresh sheet of paper and show you another example. All right, let's consider this series, and we have sort of our usual question: does it converge or diverge? If it converges, then we want to find the sum, and either way, we want to justify our answer. I think for this one, I'll write out the first few terms. So if I put in a 1, a 2, and so on, this is what the series looks like. Well, first of all, let me say this is not a geometric series. The way I know that, just at a quick glance, is when you go from term 1 to term 2, you would multiply by 1/2. But then if you multiply by 1/2 again, it does not take you to the next term. So there's not a constant r that's always being used. It's like a different number each time, so it's not a geometric series. So we can't use anything about that. This series has a name. This is called the harmonic series. It's a series that actually looks very simple, but it's kind of interesting. So first of all, if we try the test for divergence, we would look at the limit of 1 over n, right? Does it equal 0? Does it not equal 0? Well, this equals 0, and that is the case where it's inconclusive. So we can't say for sure whether this series converges or diverges, at least not with the test for divergence. We need some other kind of work, and that's why I'm doing this example. I want to show you a different way we can answer this one, because it does have an answer. Every series has an answer. It either converges or diverges, and we still need to figure out which one. So let's look at the partial sums. Technically, that is what dictates if a series converges. So remember, the partial sums is when you add up the first few terms. So S1 is just the first one term, S2 is the first two, and so on. Now, before I go much further, let me say something. The harmonic series is kind of unique, and there's a strategy that I'm about to use that we only use for this series. Okay, we're basically going to derive a rule for whether this series converges or diverges. And we're just going to do something a little weird, but we only have to do it once, and then we'll establish it as a rule. Now, what I'm going to do is, I looked at S1, S2. I'm going to skip S3 and go straight to S4. There's something I want to show you here. It actually turns out that if I group these two terms together, the 1/3 and the 1/4, if you add those up as fractions, with a common denominator, it turns out that those two add up to more than 1/2. So I'm going to say altogether this is greater than 1 plus 1/2 plus another 1/2. 1 plus 1/2, that this thing in parentheses is greater than 1/2. I'm then going to skip to S8 and do something similar. Well, S8 means we need a lot of space. I'll start writing smaller. I'm grouping those two terms together, which we already kind of established that that's greater than 1/2, and then I'm grouping these terms together. It turns out that this entire number is greater than 1 plus 1/2 plus 1/2 plus 1/2. Okay, let me tell you the pattern. I'm just going to say etc. The S's that I chose to look at, S1, 2, 4, 8, the next one that we would look at would be S16. We're looking at powers of 2. 2, 4, 8, 16. And then we start grouping together some of these fractions, and an argument could be made that this has to be greater than 1/2, this is greater than 1/2, and then if you kept going, that pattern continues, so that in general, S, I want to say a power of 2, so let me say 2 to the n is greater than 1 plus a bunch of copies of 1/2. Now, how many 1/2s are there? Here there was a 1/2, here there were 2 of them, here there were 3 of them. Notice that 8 is 2 to the 3, and there were 3 of them. I could say there are n copies of 1/2. So if we keep going, if we did S16, S32, and so on, you would keep adding more 1/2s forever. And because of that, this limit goes to infinity. It's kind of a weird argument, and we only use it for this one case, this one series. But we're going to establish that this means the sequence of partial sums is a divergent sequence. I should have said is. Therefore, the sequence is divergent. So the series diverges. So this series, which has a name, the harmonic series, we just did kind of a weird set of steps, but we're establishing as a rule that that series diverges. And we don't have to do these steps ever again. We wanted to see it once so that we'd be justified in using it. From now on, if you ever see this series, you could just say it diverges because it's the harmonic series, and that's what the harmonic series does. All right, now I have some more rules to show you. Got a theorem here. All right, we have a theorem that says if a series AN and a series BN are convergent, then so are the series, oops, this should be a BN. Let me fix that, actually. I need to make that a B. I want to say if we add the terms together, we get a new series by adding those together, and that also converges. If you subtract and if you multiply by a constant. Furthermore, this theorem says that these series would also converge, but it's also going to tell us what they add up to. I'll write these with a 1 and infinity. By the way, when we first talked about series, I believe we said this, but sometimes when talking about series, we leave off the n equals 1 and the infinity. They're sort of implied if we don't write them, but I'll write them here. This adds up to the first series plus the second one. I think if you think about it, this kind of makes sense because a series is just a lot of numbers with plus signs in between them. So there's an awful lot of plus signs going on, but it's okay to split them up like that. Same thing is true with subtraction. And for the one with a constant, we want to say this. We want to say that you could pull the constant out front. All right, so ordinarily in math, when you have sort of a sum, you might bring a constant out of parentheses. And we're saying it's okay to do that sort of thing even with a series, which is an infinitely long sum. You can still factor out a c. All right. All right, I know we've said a lot in this section. This can seem overwhelming at first. I have one more kind of series to show you for 7.2, and then after I show you this kind of series, then I'll give you a summary of what we've done so far. So let's move this. All right, so the one more kind of series for now, these are called telescoping series. And I think this is best shown by example. All right, so let's take a look at what this series does. One thing you might notice is this series starts at n equals 2. So I think that we've had all of our series start at n equals 1 so far, but I've probably said that technically a series could start somewhere else. You might notice the reason why this series starts at 2 is because if it started at 1, we would have a problem. If it started at 1, we would be dividing by 0, and we don't want that. So this series starts at 2. If you write out the first few terms, that's a good way to kind of get a sense of what's going on. The first term would be 2 over 3, and then 2 over 8. 2 over 15. Say that's enough. Now, by the way, if I wanted to know if this converges, I might try the test for divergence, but I can actually tell, even without writing it, I could do a quick mental check and say, what's the limit of these terms? And I can tell the limit of these terms is 0, so the test for divergence is inconclusive. And it was pretty fast for me to sort of check that out, but I can tell it's inconclusive, so we need some other strategy. You might say, is this a geometric series? It doesn't look like it, but maybe there's some way to rearrange it. Well, one way to find out is there a constant that you keep multiplying by? Like, what would I have to multiply by to go from this to this? It's kind of interesting. You could do a little scratch work to figure that out. What number would you multiply 2/3 by in order to turn it into 2/8? If you do a little scratch work, it's actually 3/8. Okay? And then what number would I have to multiply 2/8 by in order to get 2/15? It's actually 8 over 15. And because these are different numbers, it is not a geometric series. So, what have we found so far? This is not a geometric series. It's not answered by the test for divergence. And it doesn't really seem like that harmonic series we talked about. So, this is something totally different. Actually, we're going to use something that we've done this semester. We did it in kind of a different context, but we're actually going to use partial fraction decomposition. You remember partial fraction decomposition, we used that back when we were doing integrals, when we needed to integrate certain kinds of functions. This was a way of sort of rewriting a function in a nicer form. And we're not integrating today. We don't need to integrate this. But partial fractions is really like an algebra trick to rewrite this expression in a different way. So that's the part of it that we'll use. You would factor the denominator. This does factor. n plus 1, n minus 1. And then set it up like this, a and b. And then we want to figure out if we could find a and b. And my idea, just to tell you what's going on, is if I could take this series, this 2 over n squared minus 1, if I could rewrite it in this form from partial fractions, maybe there's something we could do with that. Yes, there will be something we can do with that. You'll see. So, do the algebra to figure out a and b. You could try that part on your own if you'd like. I realize I haven't really had many questions for you today, so feel free at any point to pause a video and try something on your own. Maybe I'll have something to ask you towards the end. All right, this is what my algebra looks like. The system that I get looks like a plus b must be 0, minus a plus b must be 2. It's a little system of equations. All right, I get a equals -1 and b equals 1. And then let's see what this tells us. And remember, we're not integrating, so no integral symbols anywhere. But what we did find is that this series could be rewritten. I'm rewriting it slightly differently. Let me show you what I'm doing here. Because one of these was negative and one of them was positive, I swapped the order around so that the positive one was first and the negative one was second. I just thought that would be a nice thing to do. Yeah, but you could look at how we wrote it above. I'll point to it. I wrote it with the n plus 1 first, but then here I swapped the order to put the positive one first. That's all. All right, what we're going to do is now we'll write the first few terms of the series in this form. Now, let me just remind you, we already wrote the first few terms of the series. At the top of this page, I wrote 2/3, 2/8, 2/15, right? And we looked at them, and it didn't really tell us all that much. But now I have kind of a new perspective on this series. I'm like, well, this series could be written in this form. Let's write the first few terms again, and it's going to show us something different. So when n is 2, put a 2 in and see what you get. 1 minus 1/3. That's sort of my n equals 2 term gets me that. And let's leave it as 1 minus 1/3. Don't combine those yet. You'll see why. Next, when n is 3, I get 1 over 2 minus 1 over 4. Okay? When n is 4, I get 1 over 3 minus 1 over 5. And continue. That's enough. So, something interesting happens here. I mean, first of all, this looks very different from what I wrote at the top of the page when I had the 2/3, 2/8, 2/15. Although it is equal, like this equals 2/3, doesn't it? And this equals 2 over 8 if you were to combine those. So yeah, it's still equal to the same series. We're just looking at it in a different way. What I want to show you is that there is some canceling that I could do. I notice that there's a minus 1/3 and there's a plus 1/3. So how about we cross them out? Minus 1/3 and plus 1/3 cancels. Is there anything else? There's a minus 1/4 and a plus 1/4. You could cancel those. There's a minus 1/5 and a plus 1/5. And doesn't it feel like this minus 1/6 probably cancels with a plus 1/6 down the line? It's like right around here. And the minus 1/7, doesn't it seem like that's going to cancel with a plus 1/7 that happens? So wait, what am I left with? The 1 did not cancel with anything, and the 1/2 did not cancel with anything. All terms get canceled by a later term except 1 and 1/2. Okay. Interesting. So does that mean this adds up to just 1 plus 1/2? Here, let me phrase it this way. Technically, we should be looking at the nth partial sum. So this is similar to what I just wrote above, but what would it look like if I tried to add up the first n terms? It's a little tricky to see this, but let's say I have sort of, this is when n is 2, when n is 3, all the way up to, okay, this is just going to be up to n. So my nth term looks like this. Right, but I left this here because I wanted to show you one previous term. So this would be n minus 1 getting plugged in. It's like sort of 1 less. What I wanted to show you is which pieces are not going to get canceled by something later. Well, the 1 will still be here. The 1/2 will still be here. Actually, this minus 1/n is going to stay because there's no later term that it cancels with. And this minus 1/n plus 1, there's no later term for it to cancel with. So this equals 1 plus 1/2 minus 1/n minus 1/n plus 1. So I need a new sheet of paper to fit this. You know that with series, technically, we should be looking at the limit of the partial sums, limit of Sn. This expression, I could say that as n goes to infinity, this piece goes to 0, and this piece goes to 0. So I am left with just the 1 and the 1/2. Yes, that adds up to 3/2. So we can conclude that this series that we've been looking at, almost everything cancels except the 3/2. And we would say that the series converges. It converges to 3/2. So it's kind of a weird kind of series, but it's interesting. You use partial fraction decomposition. It kind of shows you a different perspective on the series, and then when you write it out, you start seeing all these terms canceling. Now, I'm going to say it's up to you. Which of these two ways would you rather write it? Do you want to write it the first way I did with numbers and do a lot of crossing out? Or do you want to write it as the nth partial sum and do it this way? I'm fine with either one. I don't think you need to write both. And honestly, I would probably just write the first one. I'm satisfied with this. You kind of, if you can tell that everything is canceling, except for maybe a couple of things at the beginning, then you could write this. But I wanted to show you it with the partial sums at least once, because technically that's the reason why you're left with just 3/2. Now, it's called a telescoping series, I guess, because I think you're supposed to imagine it like one of those collapsible telescopes, like a spyglass, right? That you have this big expression and then it sort of compresses. Collapsing spyglass is sort of what I'm imagining. All right, so let me say something about this, though. When we canceled most of this away and we were left with the 1 and the 1/2, what will happen in a series of this form, a telescoping series, is you'll be left with something. It's not always going to be a 1 and a 1/2, but it's up to you to figure out which terms don't have a partner. Like this 1/3 did get canceled, and the 1/4 did get canceled. But in some other problem, there might be 3 terms that stick around. In this one, there were only these 2 terms left. But yeah, you have to kind of write this out to figure out which pieces are staying. Here it was the 1 and the 1/2. Ultimately, you're just adding them, and there's nothing else. All right. Now, I do want to give us a summary of this. Has been a very big section. So let's say summary of series so far. Given a series, the main question is, does the series converge or diverge? If it converges, find the sum. Show work / explanation to justify your answer. It's very important for this chapter that you're showing an explanation so that you're not doing just like a 50-50 guess of whether it converges or not. All right, number 1, we could try the test for divergence. And we said that it's not foolproof, but it is pretty fast to try it. If the limit does not equal 0 or does not exist, then the series diverges. Otherwise, inconclusive. Inconclusive meaning it might converge or it might diverge. Further tests are needed, further work is needed. What's going to happen in this chapter is we're going to be pretty much setting up like a toolbox of different series tools that we can use. And this is one of the first ones that we can try because it's pretty fast to give it a shot. Sometimes it'll answer a problem for you and then you're done. And it was really fast. For now, maybe a step 2 could be determine if the series is geometric, telescoping, or other. For geometric, it can help to write out the first few terms to look for a constant r. And I think the example we did that with looked something like this. This is where we have kind of a times 1/3 times 1/3. Right? If you can use the first few terms to identify a constant like that, it could help you identify that it is geometric. If you identify that it's geometric, what do you do? Well, for geometric, get it into this form and then use the rule. If the absolute value of r is less than 1, it converges. Otherwise, it diverges. So that's a rule that you have to remember, and a tiny little formula that you have to remember, a over 1 minus r. Let's get a new page here. If you think that you might be dealing with a telescoping series, it would be something that looks like you could apply partial fraction decomposition. Or you know what? Maybe if you're lucky, maybe you have one that's already factored. Like maybe the denominator's already factored, gives you a little head start. But I'll say factor the denominator. And use partial fraction decomposition. And then write out terms and look for cancellations. Right, that was the main thing we did, is we sort of looked for what gets crossed out and what remains. Now, when I said to determine if the series is geometric, telescoping, or other, here's an example of other, the harmonic series. Let me say the harmonic series. There is only one. The harmonic series is that the series 1 over n diverges. That's just a rule that we can use. Now, the truth is, I'm probably not going to give you the harmonic series exactly and just ask you, does this converge or diverge? Because, we've said today it diverges. What you might see, though, is you might see the harmonic series appear in some other form or appear within a problem. So I'll show you an example in just a moment. What we've just done in the last page or so, I think, is a good summary so far. And throughout the chapter, we're going to keep adding more to this. There's just, the series is going to get bigger and bigger. For now, we've only seen a couple of types of series, so there's definitely some problems that we can't do yet. But yeah, that's the main idea, is we want to know, does it converge or diverge? And we've seen a couple of different forms. So I'll show you 2 more examples to wrap this up. All right, here's an example. And you know what? You could pause this and you could try this one on your own. It's the usual question. Does it converge or diverge? If it converges, find the sum. All right, so this one is actually pretty fast. What I wanted you to notice is that this is equal to 5 over n is the same as 5 times 1 over n, right? So 5 times 1 over n. And we had that rule that said a constant can get pulled out front. So this is one example of how you might see the harmonic series show up within a problem, even though what I gave you wasn't exactly the harmonic series. It is 5 times the harmonic series. Well, what happens is this diverges. In fact, it diverges to infinity. So we have 5 times something that's going to infinity, and we can say diverges. I'll say diverges because the harmonic series diverges. All right, the idea is that if I take something that's approaching infinity and I multiply it times 5, it still approaches infinity. All right. Let's do one more example. This one is a little bit this one's a little bit tricky. I'll say it's up to you if you want to try this on your own or if you just want to see how I talk through it. All right, there it is. I'll give you a chance to see that. So here's what I'm going to try. First of all, it has the number e. We know e is a constant, right? Isn't e a constant that's around 2.7 or so? Let's try writing out the first few terms. I actually think that that's never a bad idea, to write out the first few terms just to kind of get a sense of what's going on. What is this series? Well, when n is 1, I would get this. When n is 2, I would get this. N is 3. All right, I'll say that's enough. I can kind of see the pattern. Now, because this has an n that's somewhere in an exponent, I'm kind of wondering if this is a geometric series in disguise. Like, it doesn't really look like a geometric series because it doesn't have an n minus 1, but maybe there's a way to get it into that form. So I'll ask myself, is there a constant that I would keep multiplying by to get from one term to the next? And I think there is, because look at how these terms are changing. To go from 1 over e squared to 1 over e to the 4, I would multiply by 1 over e squared. And then to get from 1 over e to the 4 to 1 over e to the 6, I would multiply by the same thing. And because we keep multiplying by the same thing, that means it's a geometric series. So, geometric series we just found r, right? This is what r is. But we also found a because a would just be the first term. So 1 over e squared and 1 over e squared. So I could use my rule for geometric series. Let's figure out what is the absolute value of r. We have to figure out if that's less than 1 or not. Well, let me write it this way. It's approximately equal to 1 over 2.7 squared. Well, you don't have to know exactly what e is, but you should know that it's in that neighborhood. Whatever this decimal is, I can tell that it's less than 1. That's all I need to know. Is it less than 1 or not? Yeah, this is less than 1. So the series converges. I'll put a box around that. And it converges to a over 1 minus r. Let's figure out what that is. So 1 over e squared for a, 1 over e squared for r. We see sometimes a and r might be the same thing. How do we want to simplify this? I've got an idea. I'm going to erase my equal sign here. I want a little more space. I have an idea to simplify this fraction within a fraction. How about we multiply by e squared over e squared? I think that'll clean this up a little bit. That will make the numerator 1 and the denominator e squared minus 1. I think that looks nicer. I think that looks much nicer. All right, the series converges to that. I mean, you could figure that out as a decimal with a calculator, but we don't really need to. I like this. This is exactly what the series adds up to. All right, well, that was my last example. This wound up being a really long section. Hopefully the summary that we did a couple of minutes ago, hopefully that was helpful. One last thing I'll say about this section is remember to show work, but another thing is make sure that you clearly state your answer. Does it converge or not? Yes, I'm making it very clear that I'm saying it converges. Did I find the sum, right? I think it's a good idea to circle your answer or put a box around it. The reason I'm saying that is in the past, in previous semesters, sometimes I'll have a student who does beautiful work, but then it's not really clear. Are you trying to tell me that it converges, or are you trying to tell me it diverges? So you have to have that word somewhere. Yeah. All right, well, let's say that's it for now because we've gone on for a while. And as always, feel free to reach out to me if you have any questions. And I hope you're doing well. I will see you soon. Bye.